morning session of Big Proof 3. Very happy to have Angeliki Koutsoukou-Argyraki, and she'll be telling us about a bit about the Union-Closed Conjecture. Over to you.
Okay, thank you very much. I hope the sound is all right. Let me know if you can't hear me. My voice is not very good today, so apologies, but I'll do my best. All right, so I'm very happy to be here. This is my third Big Proof event. So I would like to thank the organizers and all the participants and speakers so far. I have been learning a lot the past few days. So I attended the first Big Proof conference at Cambridge in 2017. It was in this very room, actually. And back then, I hadn't tried any proof assistance so far. So I was fresh out of my PhD in pure mathematics and applied proof theory. And I joined the formalization community shortly afterwards, after that, in autumn 2017, when I joined Alexandria, which ran from 2017 until 2023, led by Larry Paulson, who's sitting right here with us. So this is a screenshot from Larry Paulson's webpage. And yeah, I'm very grateful to all my colleagues for all the interesting work we did so far during 6 years of Alexandria. So I'm very excited to be here today and see all the progress that has been made the past few years in the community. The community has grown a lot. So back in 2017, when I joined, Lean was just starting. It was a very new thing. Since then, we've seen a lot of big developments in AI as well. So the picture is completely different. And I think we have exciting things ahead. So usually I like to start my talks with my original personal motivation to formalize mathematics. I've talked about this many times before. So my original personal motivation when I joined the formalization community. So due to my background in applied proof theory, proof mining, and applications of proof theory to nonlinear analysis, extracting computational content from proofs, my original motivation personally was to gain insights into the nature of proofs when I started formalizing. But of course, as we all know, there are many other important advantages to formalizing mathematics. Obviously, verification, eliminating mistakes, reliable refereeing. So it is conceivable that in the future, maybe in the near future, when submitting a paper to a journal, we will be submitting it along with the formal proofs. So this could speed up the reviewing process. Of course, it could help with building useful educational tools as well. When it comes to large collaborative projects, again, this is an argument that has been mentioned many times. We've seen it in practice in many interesting, striking projects. We can help this. It can help with bookkeeping. So all the details of a proof are more accessible. So when a lot of collaborators work on the project, it's easier to coordinate. It's easier to keep track of all the details in a big, complicated proof, and it can help with collaboration on in research-level mathematics. Of course, these are arguments that have been mentioned many times. I think we are all well aware of this. I don't think I need to convince most people in this room about the benefits of formalization. A couple of more comments, of course. When we use new tools, even in a setting that is familiar to us, we are forced to think things from a different point of view, from a different angle. So this can lead us to deeper understanding and new mathematical insights, perhaps. So when we have to explain a proof to a computer at a high level of detail, we are forced to think and rethink proofs and definitions. So even familiar material can be seen in a new light when using new tools, right? course, so preserving mathematical knowledge in big libraries to formalize mathematics, that's a very big thing today. Essentially, we are building databases with an enormous potential for the creation of future AI tools to assist mathematicians in the discovery of, or invention, whatever you prefer, of new results. And I say future AI tools, and we've been saying this for some time, but maybe this future is already today, or at least it's closer than we recently thought. So when we have proofs written in code, code is something alive, we can modify it, we can play around with it, remove a lemma, see where the proof breaks, we can directly interact with it, recycle it, recombine it, and have this direct interaction that can be very useful and insightful. But I will be coming back to the creation of future AI tools. So a vision for the future of research mathematics, I think this is a vision that many of us share in this room, is to create an interactive assistant that would help research mathematicians in the creative work in all these ways, right? And we've already seen several talks in this conference already towards this direction, right? And I would say, at least for me, the goal is to assist mathematicians, of course, not to replace them. And again, this future may already be today or quite closer than we think. Okay, so without further ado, let me tell you a bit about the Union-Closed Conjecture. So, first things first, we say that a family of sets is union-closed if the union of any two sets from the family belongs to the family. So yeah, we take them pairwise and we see if the union belongs to the family, then the family is said to be union-closed. So the Union-Closed Conjecture, or the Union-Closed Sets Conjecture, as we might see it in the literature sometimes, was introduced by Franklin in 1979, and it says the following. For every finite union-closed family of sets, other than the family containing only the empty set, there exists an element that belongs to at least half of the sets in the family. So it's a very beautiful and simple statement. To give you a simple example, just for some intuition, we have here this family of sets. It consists of 5 sets. We can tell that it is union-closed immediately because if we take any 2 of them, right, their union belongs to the family. And we see immediately that the conjecture holds. So for example, take element A, which is in 3 out of the 5 sets of the family. Okay? So there are proofs. There is also some recent progress, actually, that I'm not mentioning today. But so there are proofs for several special cases of the union-closed conjecture. So special cases of specific union-closed families. But the proof of the general case is still elusive, despite the simplicity of the statement, which makes it even more exciting, right? It's a very simple statement, but yes, we have yet to find a proof for the general case. So there is this theorem by 2021 that Larry Paulson, who's sitting right here, and I formalized a few months ago. So here is what this theorem says. It's a theorem by Arason, Ellis, and Leader, published in 2021. So this is the reference here. So the statement says that the union-closed conjecture holds for the union-closed family generated by the cycling translates of any fixed set. So the proof is very, very beautiful, very elegant, and surprisingly short. You'll be surprised to learn that this is just 1 page and 1-page proof. And yeah, I would say it's an extremely elegant and beautiful proof. And it is surprising given that this is such a quite strong statement, right? And the Isabel formalization is similarly very short. It's only about 270 lines of code, right? And this is a reference to our formalization. It's on the archive of formal proofs. So Larry Paulson and I formalized this in Isabel. And the reason that the Isabel whole formalization is also quite short, I mean, of course, the proof did not require a lot of prerequisites, but part of the reason was that the main prerequisites for these were already formalized and they were available on the archive of formal proofs. And the main prerequisites for this proof had to do with subset theory. So let me tell you what a subset is. So let A and B be finite subsets of an abelian group. We say that the subset of A and B is this set of all possible sums of the elements, all right? Nothing more complicated than that. So Larry Paulson and I had already developed all the essential prerequisites when it comes to subset theory in this entry here on the archive of formal proofs from 2022. We developed this with the purpose of formalizing the Bruner-Kerusa inequality. And this was built on an algebra library by Ballerin from 2019. All right? And as a side note, there are more developments on the archive of formal proofs in additive combinatorics that has to do with subset theory, properties that have to do with the size of subsets, which builds on subset theory that was developed in the Bruner-Kerusa inequality AFP entry. So we used the subset theory material to formalize more results in additive combinatorics. With Larry Paulson again, we formalized Kovansky's theorem. With Mandas, Baksis, who is also here in the room, and Chelsea Edmonds, we formalized the Balogh and Moredi-Gowers theorem. See Tim Gowers here. And again, with Mandas, we formalized Kneser's theorem and the Cauchy-Davenport theorem. And I have a brief summary of these formalizations in my invited talk at ITP in 2023. So there's a brief summary about these formalizations. But now let me go back to our main topic, the special case of the Union-Closed Conjecture that we formalized, the theorem by Arison, Ellis, and Leader. So now that I've told you what a subset is, I can show you how the statement looks like. So let G be a finite abelian group, and let's fix a subset of G, which is non-empty. And we define this family in this way, which is the set of all unions of translates of this fixed set R. Okay? Then the statement says that the average size of a set in this family is at least the cardinality of G over 2. In particular, the Union-Closed Conjecture holds for this specific family. So this is how our statements look in Isabelle, right? So the first part, we have it as a lemma, which tells us that the average size of a set in the family is at least the cardinality of G over 2. And this is, of course, very packed. It says that, well, we show that the Union-Closed Conjecture property holds for this family F. You will see this F is in black, so this means that it is already fixed, predefined. So in order to state our statement like this, of course, we have already defined, we have fixed some things in our theory. So we start with a locale, where we fixed this R and this G, and the assumption that this R is non-empty, all right, and that G is finite. And we define here what it means for a family, for any family, to have the Union-Closed Conjecture property. Okay? Now we fix this specific family, we define it like this as the neighborhood, which is defined on the power set of G. Maybe I should go back and show you the statement again, okay? And this neighborhood has been defined like this, right? So it is easy to see that this family that we are working with is indeed union-closed. And the argument to see this is that for any pair of subsets of G, we have this here, this equality of sets for this union, right? So having defined the definition of what it means for a family to be union-closed. You can see here the definition, right? We prove in this little lemma, union-closed F, that this family is indeed union-closed, right? So we're working with a union-closed family. So this is the statement here, and it's a very, very short and straightforward proof, okay? Okay, now let me tell you a bit, let me sketch for you the proof of the theorem. So first of all, for any subset of G, we defined the R interior of this subset A, right? In this way, and this is how it would look like in Isabelle. Just to show you a bit of Isabelle syntax. And we define a function, we call it little f, from the power set of G to the power set of G in this way. Again, this is written here in Isabelle syntax. And it is very important to show this inequality about cardinalities, okay, for all subsets of G. So yes, this is the first important argument to prove here. And then the key step, I'm not showing you in detail how this key step is shown, but the key step is to show that the restriction of this function at the family is a bijection, actually, from the family to itself. And of course, yeah, it satisfies this inequality. And therefore, because we have this bijection here, we can write this here because of the cardinalities are equal, right? And by the inequality, we see this immediately. So this completes the proof of the first part of the theorem. Yeah, that says that the average size of a set in this family is at least the cardinality of G over 2. Okay? So this is less than 1 page, without too many things to fill in. And now let's see the second part of the theorem. So we have a key argument which has to do with counting elements in 2 ways. So it's a key counting argument which is intuitive to see, really, but to show this in Isabelle, it's a bit more time-consuming. So, well, we can immediately see that take an element X in the group G, right, and count in how many sets of this family it appears, yeah, like how many copies of this, and then sum over all elements of G. And this is equal to the sum of the cardinalities of all the subsets, of all the elements of the family. Sorry, yeah. Yes, all the sets that are elements of this family, right? So you sum the cardinalities. So you can, yeah, to gain some vision, you can just try it with in a schematic way. It's very easy to see, but in order to explain this to Isabelle, it's quite tricky. So it takes a proof by induction, and it takes roughly 28 lines, I counted. And now from the above statement and the first part, right, it's just a matter of rearranging these terms. And we, yeah, divide by some factors here, using this and the previous inequality, right? And we get this inequality here. And then all that is left to do is to show that the Union-Closed Conjecture holds by a proof by contradiction. So assuming that the Union-Closed Conjecture does not hold, we have an inequality which is, it says here is this quantity here is strictly less than 1 over 2. Right, so contradicting this, and then we get a proof by contradiction. So this takes about 25 lines in the formal proof. I think I will be showing this proof by contradiction later on in the second part of my talk. So it is interesting that the proof of the second part of the theorem, it is not spelled out at all explicitly in the paper because it is quite straightforward. But in Isabel, it needs a bit of work to be, we need a little bit of work to complete this. So it is roughly, less than 60 lines. But in the original paper, this argument is just one line, right? But the whole proof is just one page, like I mentioned before. Okay, so I will show a few more little things about this proof in the second part of my talk, like I said before. But before I move to the second part of my talk, please allow me to show you something that made me feel very, very excited when I was about 12 years old or so. So this is not mathematics. I know some people think these are math formulas, but they are not, believe me. This is a text in ancient Greek. And this was the very first text I encountered in middle school when we had to learn a bit of ancient Greek at school, right, the very first one. But that's not the only reason why it made me feel so excited. I will explain to you why shortly. So I know you cannot read this. I will tell you what it says. But I have translated the part in bold here in English. So that's the part in bold. So this is a myth by Aesop, the famous storyteller of antiquity. He lived around 600 BC. And if you haven't heard of Aesop, you've probably heard of other stories by him, like The Tortoise and the Hare, or The Boy Who Cried Wolf, right? So this little myth here says that they say that the animals were created first, and they were given different gifts. Some were given strength, some were given speed, some were given wings to fly, but the human didn't have any of this. So he complained to Zeus, the father of the gods, and then he replied, you cannot feel, you cannot understand the gift, even though you had the luck to receive the greatest gift of all, which is logos. Logos is here conjugated, which has power among gods and humans. The strongest of the strong and the fastest of the fast. Okay, this can make it the strongest of the strong and the fastest of the fast. And then it continues to say that, only gods and humans have this gift, but not animals. And it's a shame for those who have been blessed by this huge gift to be envious for the silly animals that do not possess this gift. Okay. So what is logos, this great superpower that humans have? So it means different things in ancient Greek. It means language, speech, word, thought, reason, reasoning, logic, computation. The word logic is derived from logos, quite obviously. And it also means the ability to speak, the ability to think, the ability to reason, the ability to compute. And according to Aesop, this is what differentiates humans and gods in this little text from animals. And of course, there is an interesting discussion that could follow. Well, even Aesop would be surprised how accurate his little story is today. Well, I mean, humans may not have wings to fly, but they can invent the wheel and speak to each other and develop culture, develop technology, develop civilization, develop mathematics, engineering, and eventually build planes and fly, right? Without needing to have wings, and fly even faster and higher than birds, okay? Now, if you look this up, it says it is derived from a verb that means to collect words, right? To reckon, to say, and it means that what is said, that what is thought. So word, sentence, speech, story, debate, that what is thought, reason, consideration, computation, reckoning, an account, explanation, narrative. And it is such a powerful term that it actually appears in other contexts like philosophy and theology, okay? So it is, such a powerful term that you might have seen it 600 years after Aesop. It appears in this other well-known text. This is from the New Testament. It reads, "Αναρχήν είναι ο λόγος, και ο λόγος είναι προς τον Θεόν, και Θεός είναι ο λόγος, and here logos is translated as word, okay? But, I mean, my only point here is to say that it's quite striking that even though ancient Greek has a quite rich vocabulary, the same term is used to describe language, speech, word, thought, reasoning, logic, and computation. The ability for all these things, the ability to speak, think, reason, and compute. And this doesn't seem to be just a case of simple polysemy, because in certain contexts where it is used, it's not clear. It doesn't mean just computation, but it means both language and computation, like in the little myth that I showed you. So well, as a 12-year-old, I was very intrigued when I first learned about logos and its multiple meanings, right? Or maybe these are not multiple meanings, maybe these are aspects of the same concept. So yeah, I wanted to share this with you. I found it quite striking, at least back then. And nowadays I think of this quite often, because nowadays I'm even more intrigued because large language models, okay? And all this impressive work that has been done recently, very promising progress, a lot of work on formalization recently. So many people here have already described some impressive work in this direction. So given this, I think it makes a lot of sense to see formalized mathematical material as datasets. So this brings me to the second part of my talk. So I want to return to this vision for the future of research mathematics, right? So I'm copying from my previous slide. The goal is to create an interactive assistant that will help research mathematicians in the creative work in all these ways, right, to assist mathematicians. And like I said before, my main motivation when I got into formalization was to understand, to gain insights into the nature of proofs. But then I followed a more utilitarian perspective, right, to create tools that can be useful for mathematicians in the creative work. So given all this recent impressive progress in AI and LLMs and formalizations, I think this leads us to ask the question, so how can we as formalizers help LLMs help formalizations? So seeing formal proofs as datasets, okay? So that we could perhaps help improve their performance. And I was thinking about such questions a long time ago. So this is a paper that I wrote in 2021. And this was before I'd even heard about LLMs myself. So I was simply arguing that since we are building all these big libraries of formal proofs, we can see these formal proofs as datasets in a sense, and it would make sense to choose to formalize proofs or little blocks of proofs where the computational content is made explicit, so that when it gets recombined, relying on future advances in automation and in machine learning, thanks to powerful pattern matching by machine learning, this computational content would get preserved, it would get resized, recombined, and it would eventually manifest itself in different contexts. So that was my suggestion. And of course, this is extremely speculative. I felt very awkward about writing this because very clearly I don't know exactly how this, I don't know at all how this could be achieved, right? And I still don't, but it seems that things are moving quite fast, so maybe this is not as sci-fi as I thought back then. Okay. So then back to my original question about how to approach formalization, seeing formal proofs as datasets. So we can ask this question on two different levels. So the first level has to do with organization and structure of libraries of formal proofs. The second level has to do with choices made actively in the development at a local scale while being in the process of formalizing, okay? And there are many different aspects to this. So I want to focus on the second question here. That's why it's bold, right? And there are two approaches, two answers to this question. And these two answers, I think they apply to both levels, right? But again, like I said, I'm focusing on the second level today. So the first approach, I call it laissez-faire, laissez-passer formalizing. let's simply do nothing. Just formalize what you want, the way you want it, and then let LLMs pick up whatever they pick up, okay? Simply put, naturally. Which is, I guess, what's happening until now, all right? Or the second approach, I would call it intentional formalizing. To do a bit of exploring and testing, I guess you would need a lot of computing power to do that. I will come to these questions now. First, establish and follow certain criteria, or call it guidelines, or principles, or design choices to make when formalizing to ensure readability, but this time, readability of formal proofs not for humans, but for LLMs. So, and I would be very, very interested in the experts' opinions on this. So the question of readability comes up again and again when it comes to formal proofs, but this time I'm focusing on readability for LLMs, okay? So let's see different aspects of this. So when we write definitions in a formal proof development, should we be using lambda terms in the definition or not? Should we be packing properties inside definitions, or should we write them explicitly? So for example, we could write the statement that I showed before, the theorem by Arison, Ellis, and Glitter that we formalized in this way. And here we have everything stated explicitly. We fix here our R, we assume, we fix our G, we assume it's finite, right? Subset, all the assumptions here. We define our family here clearly, and we show this statement, yeah, that the Union-Closed Conjecture property holds. So it's not packed inside this, but it is explicitly given, right? While in the first version, we defined this separately, and here in the statement, it is packed, right? And we have already defined, of course, what it means. We have defined our family. We have defined and fixed our family, yeah, actually, okay, by having defined the neighborhood and so on and so forth. That's why the statement appears so clean here, while here, everything is stated explicitly. So I'm wondering how LLMs would see that. Would it help their performance to formalize things in either way? So again, an example referring to this. Here, I showed this definition before, this little f function. It is defined in terms of the interior, right? But here we define the interior explicitly, again, using lambda term in the definition, and then we define our f like this, again, with lambda term, while in the second version, it is defined like this, which is quite uglier, but here the interior is given explicitly. So I'm wondering how LLMs would respond to these two styles of defining things. Another question is, should we be incorporating assumptions in locales, or should we write assumptions explicitly in the statements repeatedly all over? So again, like I showed before, the way it's done here, we have a locale where everything is fixed. So we state our theorem like this, where f is predefined, prefixed, while here we define our family here explicitly, and we fix R and G in the statement of the theorem itself. So as you have already probably guessed, I did this work with Larry, and Larry does things in a very, very tidy and beautiful way, while I'm much more sloppy. I'm wondering how LLMs would respond to different ways of writing things, right? Again, there may be subtle differences in chosen notation. So, for example, here, the same thing, these are logically equivalent. For the Union-Closed Conjecture property, it's written like this, right? While here, we're using a quantifier. So here it's the intersection, right? While here we're saying for all members of this family, yeah? Or, for example, other little subtle design choices, or not really choices, but not consciously chosen to, for example, here we have extra parentheses that we don't really need. Would it make any difference for an LLM? I have no idea. Then the use of automation. I see the use of automation as a double-edged sword in a way. So on one hand, it points us to useful tactics and related lemmas, right? But on the other hand, I can make proof steps cryptic. So, for example, let's say an LLM could pick up the fact that, yeah, this tactic is useful in showing this style of results, this kind of results, right? And it might be useful in a sense. That would simply be simple pattern matching, right? But it could be used, well, I don't know how it could be exploited for let's say, proof recommendation for similar proofs, for instance. I have no idea. I would like some insights from the experts here in auto-formalization and LLMs. Right, so this could be useful in this sense, pointing out useful tactics. But on the other hand, proof steps can be made more cryptic. So, for example, we have here this first thing that I mentioned before that we showed, the inequality of cardinalities, right? And the argument is very, very simple. This is the argument to show this. However, the formal proof is quite cryptic. So the first step is very, very obvious because we just unfold the definition to show this. It's just a rearrangement using the definition. But then the next step, we need to go into what these lemmas say. We need to go into what these tactics say to understand the argument. Well, here it's actually a very, very simple argument. So automation might make things less readable sometimes. So again, I'm wondering to what extent automation is helpful or not to the way LLMs pick up information. And I'm also aware that there's no unique answer to that, right? There could be many other factors that play in. Another aspect of this, again related to automation, the amount and nature of detail contained in a proof. So, for example, we have this also key step. This is a key step towards showing the what I showed before, restricting little f to the family. Then little f is a bijection, right? So we need this argument to show this, among other things. It says that the neighborhood of the interior of the subset is the subset itself, okay? For any subset A of G. And the proof is just an one-line proof, right?
So, can you clarify? So all those proofs with meta or forces are actually proofs from sledgehammer, right? You did not write it.
Yeah, there's a lot. I mean, you can see the signs that there's a lot of automation involved because they're not very complicated. Yeah, or not all of them. I don't know what you mean, all of them. Yeah, there is, for example, this thing. I think this is generated by sledgehammer, and also I'm sure these are also generated by sledgehammer. I don't know if Larry wants to add something. We've made a lot of use of sledgehammer, I suppose.
Wait, if they're both 3 in the paper, then one of them, presumably the one above.
No, this is what we have in the development, but this is the first version that I wrote, right, which is longer. I think this is the shorter, nicer version that you wrote, and this is the longer version that I have.
I can't remember.
And I am pretty sure I used sledgehammer here.
Oh yeah.
It looks like sledgehammer has been used. So yeah. But in this version, I broke it first myself into 2 steps. So here we have an equality of sets, and here I'm breaking into 2 steps, star and double star. So these are just the 2 inclusions. Here we have an equality of sets. So I'm first showing the subset and then the superset, right? And then by these 2, we have equality of sets, right? So I've broken things into 2 parts, and each part is again done by automation, and then putting them together again by automation. So here the subset and here is the superset, while here it is done in 1 step. So I'm wondering, would it be helpful for LLM to see things broken up like this? First prove the subset, then one direction, then prove the other direction as a the superset. So I don't know if this amount of detail would help the LLM or not, or maybe it could make things worse. It could overload it with too much information, and I could really, yeah, I don't know. We need a lot of testing to figure this out, if possible at all. Or maybe it is a completely naive question. Maybe it makes no difference at all. So yeah, I would like to hear people's insights about this. Another question is, it has to do with structured proofs. So again, all the things I've mentioned, all the questions I've mentioned have to do with Isabelle, right? But some of them may apply to other proof assistants as well. Structured proof in particular, well, Isabelle, it's a big advantage of Isabelle that it has structured proofs. This is the final contradiction that I mentioned before. So using this, it's a proof by contradiction to show, assuming that the Union-Closed Conjecture property does not hold, we find the other direction, and then we end up with a proof by contradiction. So it's really wonderful that Isabelle has structured proofs. I am guilty of not using them as much as I should. I use too many labels sometimes, so labeling formulas instead of using the straight-through version. I suppose that it would be very helpful for LLMs to see structured proofs. So it is a question of, but when we use labels for a formula, does an LLM easily understand? It has to need to do some to figure out that, yeah, this is the same formula that we're using, essentially. So it goes a bit beyond pattern matching, I think, this. And maybe structured proofs are more readable for LLMs. However, there might be a catch. For example, here in this proof structure, we also have ... This, of course, refers to the previous have, which is right here. But would this make things more... Would this make things less readable for an LLM, right? That's, these dots here we trace back to the previous have. So yes, these are all questions that I have about readability of formal proofs when it comes to LLMs. This time, when it comes to humans, and of course there are other aspects to it. There's the amount and quality of comments in the code. I suppose this would make a difference as well. To what extent, again, it would take a lot of testing to find out. And the names chosen for lemmas, theorems, and definitions would be an important factor, I suppose, again. And maybe other factors could play in. I don't know if you have more suggestions or things you've noticed or things you'd like to explore. So yeah, I think time will tell to what extent LLMs will be useful in formalization and mathematical practice. But in the meantime, it would make sense for us to make the best of current state of the art and try to think of formalized proofs as datasets for LLMs, and consider exploring a little bit so as to establish some formalization design choices that would make our proofs more readable for LLMs and would perhaps improve LLM performance. So that was my suggestion. So I have more questions than answers in this talk. I'm very interested in your input. So that's all I had to say. And perhaps a final little comment. So Aesop versus Turing in the era of LLMs. I showed you Aesop Smith before about logos. We saw that logos, which means all these things, language, speech, thought, logical reasoning, and computation. This was described by Aesop as this amazing superpower that differentiates humans from animals. And we know today this is not quite the case because, well, research has shown that animals as well have something like a language, some species, some animal species. They're also able to count or do some kind of computing. So it's not exactly true. But then, many years later, Turing asked, can machines think? So in AI, we are essentially dealing with the challenge of approximating human intellectual capabilities with machines. And the extent to which this is possible, or the limits to it, is still an open question. So thank you. That's what I have to say.
Do we have questions? Olivia?
Yeah, thanks for this very interesting talk. I really like the attitude of, not feeling threatened by machines, but thinking, oh, how can we help the machines help us? So that's really good. I don't really have answered all these questions, but maybe two comments, I would say. First, I think we should think of this as, it's not us who should adapt to the machines, it's the machines that should adapt to us. And when, these questions of style, what is the best style for the LLM? I think we want to teach the LLMs to produce proofs or formalization in the style that we want, and that is most readable or more useful to us. So that's one aspect. But that said, I think, and okay, you said it well, that we need to do a lot of experiment. There is no answer that we can cook up like this. But in general, having a lot of diversity helps. So if if you have a proof written in different styles, in different ways, that may help the LLM, spot more patterns. So in general, the more volume and the more diversity, that's
yes. That's very interesting. So your talk was this first attitude that I mentioned. So essentially, just formalize the way we like and let them pick up as much as they can. So the first approach, essentially, right?
We should steer towards that, because we should produce the output that we want them to imitate. But also, introduce more diversity. That's certainly helpful, and trying different styles, because maybe there is not just one style that we like, and sometimes proofs which use a lot of automation, they are useful for certain things, and proofs that are very detailed, they are useful for other things, like for education maybe. So having both is good as well.
So maybe my previous comment was not clear. What I meant is, so if what you're really doing is calling sledgehammer, then probably the LLM needs to know that this, and there could be some annotation saying this line comes from sledgehammer, and so that the LLM does not try to speed out the Metis call, but just call sledgehammer. This is simply what I wanted to say.
Maybe Larry has some comments, because we did
indeed, one of the problems with things like GitHub Copilot is that they can give you code they've seen before, but they have no idea whether it's good or not. And there's evidence that it will yield up 30-year-old code using standards that are no longer regarded as acceptable. And of course, it has no idea it's doing this any more than it knows that you really can't put rocks on a pizza, even though it found that on the internet somewhere. So I think that the input data that you provide to LLMs has to represent the quality that you want to see in any output it generates.
Can I ask a question about how you think this shifts in representation could be done automatically as some kind of pre-processing step for the LLM training? Does it have to be us humans who do these different styles by hand, or can we actually automatically, expand out sets of definitions to see whether the definitions are causing some kind of impedance problem for the machine?
Yeah, that's a wonderful question. I don't know exactly fully the answer to that, but of course, like it has already mentioned, Sledgehammer produces automatically different kinds of proofs. So there are different proofers that are called, and each of them might give you a different proof for the same statement. So already there's automation giving us alternative proofs for the same statement. Well, sometimes they're quite similar, or almost the same, or completely the same. Well, by doing that, well, I don't know. I would guess there might be a way, but I'm not the expert to. It would be good to do that, yeah. But then maybe it has to do with the formalization, and for the formalization, we need to, as far as I'm aware, we need to check for semantic correctness. So if well, even if what is produced is compiled, so it's syntactically correct, we need to check for semantic correctness that it actually says what we want to say, like if it's the same mathematical meaning in the statement. So, but maybe the experts on formalization have the answer to this. I don't know. I would like to hear more comments, or maybe later if someone wants to discuss. That would be very interesting for me. For your question.
One issue in coding with LLMs is that they hallucinate packages, right? They will make up these problems, and that seems like basically the same issue as them maybe making up plausible-sounding lemma names and things. And your suggestion was to use the correct, to use good labels that are sort of intuitively obvious. What's the implication from this? Should we go back and rename old lemmas with more plausible sounding names so the language models are more likely to get them right? Or?
Well, going back and redoing things, that would take, I don't know how many years or effort. I wouldn't suggest that. But also this, thank you for your comment, because it's, of course I should say that there is a vast amount of information online, and LLMs are trained on everything that is on the internet, so this is a huge amount of information already there for them. So if we start to do things differently, I don't know to what extent this will make a difference in the grand scheme of things. This does not answer your question, but it's related to what you asked. Right, so I wouldn't suggest going back and rewriting all the libraries of formal proofs. That would be a huge amount of effort. But maybe starting doing things differently from now might make a difference. Maybe not, given all the vast amount of information we already have. But I think it might be worth exploring. I don't know. Or another reason why I didn't mention that in my talk, but another reason why I think it is worth exploring is that it might give us some hints as to how LLMs work from the inside, which is another research question I'm very interested in. So maybe you have some comments about this.
So, for the problem of hallucination, I think right now the best way to solve it is to use this interaction, like allow the LLM to look up data or to fetch documents or pieces of code and read them as it processes the data. Because it's true that we can't bake all the information into the weights of the LLM, and so far, techniques like RAG, the retrieval augmented generation, where you allow the LLM to do lookup in the database and use the documents that come back to produce the answer. These tend to work well for removing hallucinations. So, for looking up, even if the name of a lemma is obscure, as long as the LLM can, read previous code and figure out, that's the lemma I need to use, and starts reading it, that would fix a lot of the issues.
You can already do this, right? I mean, you can tell an LLM, give you lean code, it gives you lean code. You say, before I even look at the lean code, look up the name of every lemma you said online. And if it's allowed to look on the internet, it'll look up Mathlib docs and say, sorry, I said this.
There. It's just a matter of plugging things together.
Yeah. So there's some simple agents that use tools that go in and look this up and get rid of this issue. Yeah. I don't think we have to rename it. As you said, the LLM should come to us, not the other way around.
This is related to what I asked about labeling formula. So I'm labeling this, I call it A, and then I use it later on in a lemma. And I'm wondering if this is too confusing for an LLM to figure out, or if it's better to not label formulas and just use structure proofs, which are very nice and very readable and very modular. So,
I guess, if you add more language into the proof, like comments, for example, that's very useful because it is for the search part.
Yes.
The LLM can look up based on some text and figure out that.
Yes, I was mentioning.
The good thing is that it's also useful for humans to add comments to code. So.
Yes, absolutely. With my colleague Yanos Athopoulos, we built a search engine for Isabel once called Therapist, and it's so Yanos was especially designed to pick up as many comments as possible, and that helped a lot when we did testing. Yes.
Do you think there could be a danger that we rewrite lemma claims to be more intuitive, let's say, that it wouldn't make the problem of hallucination better, it would make it worse, that the LLM would be more likely to use hallucinated lemma names and everything?
You mean if the name is a bit more
Yeah,
cryptic?
if we made a concerted effort to make up more intuitive names, it would be more likely that, let's say, if it's trying to put old lemmas in an old part of the library which hasn't been updated, or if it would just learn to kind of these plausible names that don't respond in the library.
And I think that's an excellent question, actually. Yes. So the answer to this, the true answer to this is really I don't know, but I am assuming. So, for example, in Isabel, things are much more liberal, right? So you can just choose to name things the way you prefer, the way you find. Yeah, it's all up to you how you name things. But in Lean, as far as I know, I don't use Lean myself, but I know that things are more streamlined. There are very solid rules. I think the Lean experts would say that how you name things, and I think the mathlib editors have some strict criteria about naming, right? So maybe this could be this strict criteria. This could be given to LLMs not as something to discover, but as hardwired rules. Let's say that. So in LLMs that combine maybe pattern matching, but also some symbolic approach to it, in the sense that we feed it with some rules, like a knowledge base that says, yes, if you name this in this way, it means this. So just as hardwired facts that these are our conventions when it comes to naming, and these conventions are always followed and are strict, that would maybe help it if we have LLMs that are hardwired with some rules when designed. I don't know if maybe you have more.
Yeah, I guess this indeed could help, but on the other hand, like as you pointed out, they are very good at picking up patterns, and these kind of patterns, these are the things that they really easily pick up from looking at the code and like figuring out that whenever there is something using equality, it's EQ or something. So then they would tend to generate names that follow the guidelines, almost automatically. Doesn't mean perfectly, but at least with very limited effort, they pick up those patterns.
So this means that no matter how they work, the more strict approach that is followed in Lean with strict rules about naming is in any case more useful than, I suppose.
I guess it's kind of lucky that the mathlib people chose, presumably the choice to have very strict naming conventions so that human beings can easily guess what the name would be, right? But it turns out it's actually also useful for LLMs to be able to guess as a result.
But then this means that the Lean people have already done what I'm essentially. Oh, this is not.
It was not invented by.
Yes, but
this idea of having names that are systematic. And if you look at MathComp, the mathematical library of Roth, this is where this comes from, and then probably it comes from elsewhere before.
Yeah. So these design choices that I suggest have already.
A funny thing about MathComp, actually, they have to follow, as far as I understand from George, they have to follow this naming because search in code was really bad. So actually, I think these days, this is still really bad, by the way. It's in my opinion, sorry, but I think it can be improved. It's a bit slow, for example, but if you have, I think these days, you will have some kind of suggestion system that, so, that was a mnemonic, no? Like addition for natural distribution, no? You have a commutativity, no? But I think these days, your interface will give you, and for the agents too, should give you, look at your code and say these are the lemmas you have to, they're here, right? So name is not so important, I think.
There's a nice paper that actually produces the names of the proofs if you give it a statement.
Yeah. Sorry.
Well, we should stop there so time for the next speaker. But thanks very much again.
Thank you.